All right, 1110 students, this video is going to complete the material that we're going to cover in Chemistry 1110, and it's more on solids and liquids and the changes they undergo. So the first thing we're going to look at are phase changes, and phase changes, well, a phase in a homogeneous part of a system is separated from the rest of the system by some sort of well-defined boundary. So, in other words, it's a glass of water. It is separated from the air above it because intermolecular forces cause that water to have surface tension that sort of closes that off from the glass and the air above it. Um, so substances can change from one phase to another. Water can boil, so it can go from a liquid phase to a gas phase, and this is called a phase change. And here are some examples: freezing water, evaporating water, melting. That's also called the process of fusion, so melting water, solid to liquid. Condensation of a gas going to a liquid. So here's a couple of vocabulary words you may not be real familiar with. Fusion and condensation, you need to know those. And sublimation, you may not have heard of this. This is where a solid goes directly to a gas, and that's what you see with dry ice. Solid dry ice goes directly to a gas phase, CO2, which you can't see, but it's extremely cold. And what you do see is the water vapor in the air, which is crystallizing. So, it's easy to make CO2 look like it's generating smoke, like in a witch's cauldron. All right, this diagram just shows you 6 possible phase changes. And so on what would be considered the y-axis, the temperature is going up. And so if you're looking at those red arrows, you could think of ice is melting, going to a liquid, then the liquid's going to a gas. And they have a diagram sort of in the middle of just using bubbles. But you can also get sublimation. The question is, does water ever sublime? And in fact, it does. If you live somewhere up north that gets a lot of snow, say Minneapolis, North or South Dakota, you get a foot of snow, and what you see after a week is there's really only like 10 inches left, and that's truly because that snow will sublimate. It will sublime into the air, which is extremely dry. All right, so we're going to talk about boiling point. The boiling point is the temperature where a liquid undergoes a phase change, going from a liquid to a gas phase. And here's some boiling points of different materials. Argon, which is a noble gas, has a very, very low boiling point, minus 186 degrees C, so that's something we always see as a gas, and its delta H of vaporization is very low. It wants to exist as a gas, whereas water, you have to get it to 100 degrees C for it to boil, and you have to put quite a bit of energy into it, 40.79 kilojoules per mole. That delta H of vaporization that's listed there is the amount of heat that you'd have to put into a mold to get it to totally convert from liquid to a gas at its its boiling point temperature. All right, another sort of characteristic of a liquid is its critical temperature, and that's defined as the temperature above which its gas cannot be liquefied. The critical pressure is the minimum pressure that has to be applied to a liquid to liquefy a substance at its critical temperature. So there's a critical temperature and a critical pressure that are important. And it's very interesting. If you take a gas phase substance such as argon, and you make it a supercritical fluid, meaning it acts like a liquid, has a lot of interesting solubility characteristics, and this is actually used in some science. So it's kind of an interesting table. We can also have liquids and solids convert from one to the other, and so going from a liquid to a solid is freezing. We're familiar with that terminology, but when something melts, it's called fusion in the science world. So the melting point is the temperature at which the solid and liquid phases can coexist. So the thing to think about is a glass of ice water. The ice and the water are coexisting, so that's going to coexist at that melting point, or you can call it freezing point, which is 0 degrees C. So whenever you have a glass of ice water, whether it's in the winter or it's in the summer, that glass of ice water is always going to be at 0 degrees C. And so here's our example of equilibrium as our ice going to liquid water. And we can write it like this. And you'll notice we use a double arrow because that's a dynamic equilibrium, which we talked about at the beginning of the previous video on chapter 12. All right, this is called a heating curve, and this is extremely important. And we'll do a couple of problems where we look at heating curves to figure out how much energy is required to go from one point on this curve to another. So what we have here at this particular time, 0, let's say, and this temperature, we have solid material. Its temperature is going up, and as it goes up, its temperature is increasing. It's heating at a certain rate, and that is that specific heat or heat capacity. Then when it goes from a solid to a liquid, is it actually melting, and that all happens at the same temperature. So that glass of ice water that we talked about, if it's mainly ice or if there's just a couple of little slivers of ice left, is still 100 degrees or 0 degrees C, because that process takes place at one temperature. And so the heat that you're putting in here, the delta H, is based on that heat of fusion and how much material you have. Then once you have the liquid, you can heat it back up. Once again, heat capacity. Then you can vaporize it. And so we have the delta H of vaporization. It all occurs at one temperature. That's why it's flat. If this were water, that would be 100 degrees C. And then you can heat up the vapor to higher temperatures. And this is why a steam burn is so much worse than a boiling water burn, because they have different amounts of energy in them, which can be converted to your skin as an actual burn. All right, so here's molar heat of fusion, various things, what it requires to melt a mole of this solid. And so very, very little to melt solid argon. If you could get it, it melts at minus 190 degrees C, so you're not apt to see it. But you compare that to something like mercury, which is a very heavy, dense liquid, or water, you see there's tremendous difference in the heats of fusion. All right, we're going to talk about that other phase change, sublimation. It's not as common, and the opposite is deposition. So it's going directly from a vapor to a solid. And there is a molar enthalpy of sublimation, so it's amount of energy per mole. And so the example I have here is that iodine. Again, iodine is an element which exists as a solid and goes directly to a vapor, so it sublimes. And if you think about that process of sublimation, if you go back to that chart where I showed the 6 different phase changes, it is similar to melting something and then vaporizing it. It's just that these atoms don't actually go through both processes, but that enthalpy of sublimation is equal to the combined enthalpy for fusion and vaporization. All right, and this is the other topic of interest in this chapter, and this is phase diagrams. And it summarizes sort of the behavior of a substance, tells you the conditions under which it is a solid, liquid, or a gas. Some interesting points here. You have temperature across the x-axis, pressure on the y-axis. So if you're at low pressures and high temperatures, you're going to have a vapor of almost anything. The solid is going to be whenever you have a low temperature and a high pressure, it's going to push those atoms or molecules together to whether they form a solid, and then the liquid exists between the two. There are boundaries, and there is something where they all come together, and that is a triple point. And that's the only combination of temperature and pressure conditions where you can have a solid, liquid, and a vapor existing all at the same time. Here's a phase diagram for water, and it is different than many things because this line, if you compare it to that boundary between solid and liquid for this generic one, this has a positive slope. Higher pressure, you get more and more solid. But if you go to the water phase diagram, very unusual because now we have a negative slope between the solid and the liquid. And in fact, what this indicates is that ice, the solid material, is less dense than the liquid. And we know that ice will melt, and that's an extremely unusual, ice will float, which is unusual for most materials. And the reason is that as the solid forms, it actually expands. And that's why we know if we want to cool down something like a Coke quickly and we put it in our freezer, we have to pay attention to how long it's been in there, because if it freezes, it will burst the can. All right, let's see what else we have. Okay, so here's a problem. We have sort of a more standard phase diagram. We want to determine the normal boiling point and melting point. So that's going to be those changes from solid to liquid and liquid to a vapor. We want to know the physical state at about 2 atmospheres and 100 degrees T or C. And then determine the pressure and temperature. That would be this triple point. So the first one, we're looking at normal boiling point and normal melting point. And by normal, what we're talking about is things that are at one pressure, or a pressure of 1 atmosphere. Remember, that's the standard where most people live in the world. And so where it makes a transition from a solid to a liquid is fusion or melting. And so we can see that for this is probably 140 degrees, about 200 degrees where it goes from a liquid to a vapor. Yep, 140 degrees. So it's saying, the melting or the boiling is going from a liquid to the gases. I said 200, it's actually 205. All right, so now what we wanted to look at was what phases it in at 2 atmospheres and I believe 110 degrees. And what we see is that it's smack dab in that purple, so it's in the solid region. And in this for C, we wanted to know where the triple point occurred. So we just draw lines to the axes and we see it's at 0.8 atmospheres, a little bit below normal pressure, and 115 degrees C. All right, that is it for chapter 12.